Take a real Mars colony, then cut Earth off completely. No rockets, no parts, no help from that moment. It's just a closed system on a hostile planet. In this video, we run through every lifeline: air, water, power, food, medicine, machines, and put a number on how long it actually lasts. The first thing that matters is timing, because Mars and Earth are only lined up for efficient cargo flights roughly every 26 months. Those are the launch windows when you can send big masses for a reasonable amount of fuel. In a normal program, you plan around that. You store supplies to bridge the gap until the next window, maybe two. Now put a hard edge on it. Earth fails right after a big shipment arrives. No more rockets next window, no more windows ever. That last cargo load is not a buffer between deliveries, it is the final delivery. The entire history of your supply chain ends on that date. From then on, every kilogram of food, every spare part, every medical device you unpack is something you will never see again unless you can build it yourself on Mars. That's the physical side, ships and crates. But there's something even more fragile than cargo, and it breaks faster: the link of information. Even when everything works, Mars is already a slow conversation. Radio signals travel at the speed of light, but the distance between the planets swings from about 55 million kilometers to more than 400 million kilometers. That's around 34 to 250 million miles. In practice, you wait 4 to 24 minutes for a message to cross space one way. You ask a question, you get an answer almost half an hour later, if you're unlucky in the orbit cycle. You still feel supported though, because there are teams on Earth watching your data, sending you software updates, looking up rare medical cases, walking you through repair procedures. When Earth goes dark, all of that stops in one instant. No more software patches, no more vendor support when the life support firmware crashes, no ground doctor to look at your scan and say, yes, that's appendicitis, you need surgery now. Every, how do we fix this, that used to go to Earth, now has to be answered locally, with the people and documents you already have. The physical distance has not changed, but in practice you go from delayed help to no help. So you are isolated, with a fixed pile of hardware and a frozen download of human knowledge. What does survival really mean in that setup? Survival on Mars is not a simple on or off switch. It is a stack of different time limits. There is the very short clock, minutes to hours for breathable air and safe pressure. There is the days to weeks clock for power. If your reactors or solar farms fail, there is the weeks to months clock for food if your agriculture breaks. Then there are slow grinding clocks, like radiation damage, wear and tear in machines, medical shortages, and psychological stress. On the International Space Station, we see how tight those clocks can be, even in low Earth orbit. Pumps clog, filters saturate, CO2 scrubbers fail, toilets break. Crews spend a lot of time just doing maintenance, and they rely on frequent cargo flights bringing new parts and tools. On a nuclear submarine, it's similar. The vessel can recycle air and water, but there is constant preventive work, constant checking, and they still come back to port regularly to reset, repair and restock. Those missions last months, not decades. On Mars, cut off from Earth, you're trying to stretch what we know how to support for months or a few years into tens of years, maybe 100. You are pushing every subsystem far beyond the operating hours we have real data for. All of this assumes you even have enough people to keep such a complex system from collapsing. That is another hard limit. A crew of 20 or 30 highly trained astronauts can run an outpost, drive rovers, maintain a reactor, and do research. They cannot by themselves be a full civilization. Long-term population models, both genetic and social, suggest you want at least a few hundred people for a self-sustaining population, and more like several thousand for real safety. You need redundancy in skills and in biology. You can't afford a situation where only one person understands the main reactor control software, or only one person can perform surgery, or only one person knows how to repair your high-pressure pumps. If that person burns out, gets injured, or dies, that entire capability disappears. With just 20 to 50 people, you are living in a mode where everyone is over-specialized and overloaded. Socially, one major conflict can paralyze the whole group, Genetically, you are forced into tight inbreeding if you try to stay there for many generations. That is not a colony, that is a very capable, very fragile camp. To survive without Earth for many decades, you want a town, not a team. That means a launch and construction effort at a scale way beyond a few demonstration missions. Even if you solve that, even if you arrive on Mars with hundreds or thousands of people and a mountain of gear, there is a deeper question that cuts through all the optimism. Is truly indefinite survival even possible with technology we actually know how to build? On Earth, people have tried to create closed life support systems, sealed environments where air, water and food are recycled almost completely. Projects like BIOS 3 in the former Soviet Union and Biosphere 2 in the United States put humans inside controlled ecosystems with plants, soil, water loops and closed air. These experiments achieved impressive recycling rates, but none of them ran for many years without outside adjustments. In Biosphere 2, for example, oxygen levels dropped in unexpected ways, and the team needed intervention from the outside. Sensors drift, materials off-gas chemicals, microbes behave in ways you did not perfectly predict. The important point is, all of this happened a short drive away from hardware stores, hospitals and specialist teams. If a pump failed, you could replace it. If a chemical filter aged badly, you could swap it. If the experiment went truly wrong, you could open the door and walk out. On Mars, a sealed system is not a research project, it is your only home. You cannot open the door, you cannot get a new filter from a local supplier. If your model of the ecosystem is even slightly wrong over a 10 or 20-year timescale, the cost is not just a failed experiment, it's people's lives. So when someone asks, how long could a Mars colony survive without Earth? The honest answer is, we do not know yet. Because we are asking that colony to do something no human group has ever done even once on Earth, in safer, easier conditions. We know that months are possible. We suspect that years are possible with careful design, but we have not proven decades and certainly not centuries. And that leads straight into the next pressure point. Because once Earth is gone, your first really hard short-term deadline is not food and is not radiation. It is much simpler, it is the air you breathe and the pressure that keeps your blood from boiling away. How long can that last on its own when the planet outside has almost no oxygen at all? So how much oxygen do you actually need just to keep people alive day after day? An average adult uses roughly 0.8 to 1 kilogram of oxygen per day just by breathing, resting, working and sleeping. Call it about 1 kilogram to keep the math simple. With 100 people, that is about 100 kilograms of oxygen every single day, around 220 pounds per day. If you want only a 30-day emergency buffer in tanks, that is about 3,000 kilograms of stored oxygen, roughly 3 tons. That is in the range of a big SUV or pickup truck in mass, and that's only 1 month, for air, not for years. Those tanks are not just heavy, they are bulky, and they are vulnerable. A cracked valve, a leaking line, or a damaged tank can take a big bite out of your reserve in minutes. You do want some storage, because it buys you time during equipment failures, but you cannot store your way to long-term independence. Tanks are a short breathing space, not a permanent answer, so the real question becomes, where do you get fresh oxygen every day when you are standing on a planet that barely has any free oxygen at all? The trick is that Mars does have something very useful, huge amounts of carbon dioxide. The atmosphere at the surface is thin, only about 600 pascals, which is less than 1% of Earth's sea level pressure, but about 95% of that thin air is carbon dioxide. To you, carbon dioxide is the waste gas you exhale, but to a machine it is a feedstock. With a solid oxide electrolysis system, you can pull in Martian air, heat it, run it through a special ceramic cell, split this carbon dioxide and dump out oxygen on one line and carbon monoxide on the other. NASA already tested this idea with the MOXIE experiment on the Perseverance rover, producing grams of oxygen per hour from that thin air. For a colony, you scale that up by a factor of millions. Instead of grams per hour, you need kilograms per hour, constant. For 100 people, you want something like 5 kilograms per hour of production capacity, maybe more. so you have margin for leaks and storage. That means large intake systems, compressors, hot reactors, filters to keep dust out, and a lot of electrical power. It is absolutely possible in principle, the chemistry is straightforward, but it is not simple hardware. If a compressor bearing fails, if a ceramic cell cracks, if your dust filters clog and you do not have spares, your main oxygen factory can go down fast. So you do not want to rely on only metal boxes. You also have another option, turning your air-based system and your food system into one loop by using plants and algae. In a good closed-loop design, plants take in the carbon dioxide your crew exhales and release oxygen during photosynthesis. At the same time, they grow food. Rough rule of thumb, under a strong artificial lighting, you might support one person's oxygen needs with about 10 to 20 square meters of very productive crops, something like a small apartment bedroom in floor area. For 100 people, that is 1,000 to 2,000 square meters of high-intensity greenhouse space, roughly a quarter to half the floor area of a big supermarket, filled with tightly packed plants. That sounds elegant, but it is not free. Those plants need water, nutrients and light on a reliable schedule. The light usually comes from high-efficiency LEDs, pulling hundreds of watts per square meter. If power drops, your light schedule slips, plant growth slows, and oxygen output drops. If you miss nutrients or let a disease spread through your main crop, your living oxygen system can stumble or crash. When Earth is available, you can fly in new seeds, new nutrients, new equipment. Cut off from Earth, you must make all of that on Mars, or risk slowly suffocating because your lettuce and wheat are unhappy. Even when production works perfectly, there is another problem, silent and constant. Mars is always trying to steal your air. Your habitat is a pressure vessel. Inside, you might keep the air at 70 to 100 kilopascals, close to Earth sea level pressure, or maybe a bit lower if you optimize the mix. Outside, the Martian atmosphere is around 0.6 kilopascals. That is a pressure difference of roughly 100 to 1. Every seal, every window frame, every pipe that passes through a wall is holding back a ton of force per square meter. Metals flex with temperature swings, polymers age and crack, dust grinds into joints. In practice, all real habitats leak a little bit. On the International Space Station, they watch air pressure constantly because even a slow leak can drain the station over months. Crews have spent days hunting for tiny leaks with ultrasound detectors and foam. On Mars, your habitat is bigger, more complex, and under greater pressure difference. You will have leaks, and if you do not find and fix them, they add up. A leak you do not notice today becomes a few % of your total air slowly escaping over a year. A small puncture from a micrometeoroid or a crack from thermal stress can speed that up to days or hours. That means your oxygen production systems are not only feeding people, they're also refilling a balloon that is always losing gas. If your production barely covers breathing but not leaks, your total pressure will drop over time, even though everyone is still alive and exhaling. You need margin and you need constant inspection and repair. With no Earth, all of that inspection and all of those repairs depend entirely on the tools, sensors and trained people already there. So here is the real bottom line on air. How many different ways can you make oxygen, and how many times can each of those ways break before you're out of options? On Mars, one oxygen system is never enough. To live without Earth, you want at least 3 all running in parallel. One path is electrolysis of water, splitting water into hydrogen and oxygen. Another is direct carbon dioxide splitting from the Martian atmosphere, like a scaled-up MOXIE. The third is biological, plants and algae in greenhouses and bioreactors. Ideally, you also keep some compressed oxygen in tanks as a buffer, and you have chemical scrubbers that can remove carbon dioxide if your biological or mechanical systems need a break. The critical point is not just do you have 3 systems, it is do you have spares for the small boring parts that keep those systems running. Compressors, valves, seals, membranes, circuit boards, temperature sensors. Each one has a limited life, a mean time between failures. Over a decade, thousands of parts will fail. On Earth, or with Earth support, you swap them out and move on. Cut off from Earth, you reach a moment where the last spare of some key component is installed, it wears out, and you do not have the tools or materials to rebuild it. The kill shot for a Mars colony's air supply is usually not we ran out of oxygen in the tanks. It is we depended on one specific piece of hardware or one specific technology chain, and we could not repair or replace one link in time. The time between Earth going silent and that moment, that is the real survival window for your atmosphere. And there is another layer to this, because both water electrolysis and plant growth depend on something even more basic than oxygen itself, a resource you have to recycle, mine, heat, purify, and protect from loss every single day, or everything else on Mars stops working with it. If keeping your air supply going already feels tight, what happens when you realize your entire oxygen system is sitting on top of your water system, and that system has its own brutal limits? Start with a basic demand. In a very efficient closed-loop system, you can push personal water use down to maybe 20 to 30 litres per person per day. That is around 5 to 8 gallons. That number includes drinking, cooking, rehydrating food, and very minimal hygiene. No long showers, no big laundry cycles, just the basics. For 100 people, that means you are circulating 2,000 to 3,000 litres of water every day, 2 to 3 metric tons moving through pipes, filters, tanks, and machines. That is the same mass as a large SUV, flowing through your system daily. That does not include the extra water tied up in agriculture, in cooling systems, in industrial process. Your greenhouses may hold many more tons locked in soil or nutrient solutions. Your radiators and equipment might use water or water-based fluids for heat transfer. So your total water inventory is much larger, but the minimum that has to move and stay clean each day is already at the multi-ton scale. If even a small fraction of that leaks, evaporates to the outside, or gets contaminated beyond easy repair, your buffer starts shrinking. So maybe you think we recycle almost everything so we are safe. But what does almost everything actually mean over years? On the International Space Station, they recover about 90% of wastewater. That includes urine, humidity from breath and sweat, and water from washing. That is an impressive number, but 90% still means 10% loss. If 100 people use 2,000 to 3,000 litres per day, a 10% loss would be catastrophic, so a Mars colony will aim for better numbers, maybe 98 or 99% recovery each cycle. But even a 1 to 2% loss repeated every loop adds up. Think about it in plain terms. If your system loses just 1% of its water each full cycle, then after 100 cycles, you have lost most of your original inventory. Real systems are more complex than that simple picture, but the direction is clear. Tiny percentage losses, plus leaks, plus spills, plus stuck valves turn into hundreds or thousands of litres gone over a few years. On the ISS, you top that up with new water shipments from Earth. On Mars, after the cut-off, that option is gone. So you cannot trust recycling alone, you have to plug into local water sources, or you will slowly dry out, no matter how good your plumbing is. So where do you get new water on a planet with no lakes you can just pump from? Orbital data and lander measurements show that Mars has a lot of water ice, especially at higher latitudes. And even at mid-latitudes, there are regions where ice sits just a metre or two below the surface. In some spots, you basically have dirty ice slabs right under the dust. That is your underground reservoir. If you can dig it, you can melt it, and you can drink it after cleaning. But mining that ice is not a simple shovel and bucket job. You are running heavy equipment in regolith that sits around minus 60 degrees Celsius, about minus 76 degrees Fahrenheit, or even colder. The gravity is only about 0.38 g, so machines handle differently, traction is poor, and dust kicks up easily. The dust itself is extremely fine and abrasive. It gets into seals, bearings, electrical connectors, and grinds them down. Any moving part you send into that environment will fail sooner than it would on Earth. To keep a steady flow of ice coming in, you need robust excavators, drills, conveyors, and storage tanks, plus a constant stream of spare parts and maintenance hours. You can try to do a lot of that with robots, to keep humans away from the harshest conditions, but that just shifts the problem to actuators, sensors and software, all of which also wear out and break. With no resupply from Earth, every broken motor and worn-out seal is another small bite out of your future water supply. Even if you can dig ice all day, there is another cost that never goes away. How much energy does it take to turn that frozen, dirty block into clean, liquid water at room temperature? Take 1 kilogram of Martian ice sitting at minus 50 degrees Celsius, about minus 58 Fahrenheit. First, you have to warm it up to the melting point, then provide the energy to actually melt it, then heat the water up to a useful temperature, maybe plus 20 degrees Celsius. In simple terms, that whole process takes on the order of a few hundred kilojoules per kilogram, roughly 300 kilojoules or more. You do not need the exact formula here. The key point is scale. If your colony needs a few tons of new water per day from ice, you are spending tens to hundreds of megajoules of energy daily just on melting and heating. Converted to power, that is like running tens of kilowatts of heaters around the clock, maybe more. On a planet where sunlight is weaker than Earth and dust storms can cut your solar output for weeks, that energy demand is not a side issue. It is a major load on your power grid. If a reactor goes down or a dust storm cuts your solar for too long, you may have enough energy to keep life support running, but not enough to comfortably melt new ice, purify it and pump it around. Then you are choosing between stretching your water thinner, cutting some industrial uses, or burning through fuel reserves faster. Every kilogram of ice you bring into the system is not just a mining problem, it is a power problem. And then there is the last, nasty twist. Even when you have melted the ice, you cannot assume that water is safe. In fact, untreated Martian water could quietly poison your colony over years. Martian soil is loaded with perchlorates, a type of salt that contains chlorine and oxygen. In small amounts, perchlorates are a serious health concern. They interfere with the thyroid gland, and long-term exposure can damage health, especially in children. Any ice mixed with soil is likely contaminated with these salts. On top of that, there may be other dissolved minerals and metals at levels that are not safe to drink. So the water you pull from the ground has to be filtered, chemically treated, or biologically processed to break down the perchlorates and remove other toxins. On Earth, you would use replaceable filter cartridges, ion exchange resins, specialized membranes, and carefully managed bioreactors to handle this kind of problem. Those components have limited lifetimes. Membranes foul, resin saturate, bioreactors lose balance and need to be reset. In a cut-off Mars colony, you cannot just place an order for new cartridges. You need a chemical industry and a biotech capability strong enough to make replacement locally, with Martian raw materials and whatever reagents you stocked ahead of time. If your filter factory falls behind, or your bioreactor crashes and you cannot recover it, your local water source can flip from safe to dangerous. So water on Mars is not just dig ice, melt, drink. It is a constant balancing act between tight recycling loops, risky and equipment-heavy mining, high energy costs, and complex purification challenges. If any one of those chains snaps, your colony does not lose water in one day. It just starts a slow slide towards shortages, organ damage from contaminants, or total system failure. And remember, every kilogram of water you manage to secure is also tied directly to your power, your agriculture, your oxygen production, and your cooling systems. If the water picture is this tight, what happens when we look at the thing that drives all of these systems at once? The energy grid that has to keep running without a single global blackout for as long as your colony exists. On Mars, a power failure is not an inconvenience. It is the start of every other system failing faster. Lose electricity, and your air systems slow down, your water stops moving, your heaters cut back, your farms go dark. The question is very direct. How stable can your power grid really be when there is no Earth to bail you out? Start with solar power, because it is the first thing most people think about. At Mars's orbit, the sunlight that reaches the top of the atmosphere is only about 590 watts per square meter, roughly 43% of what Earth gets. In simple terms, The same solar panel in the same orientation gives you less than half the power it would closer to the sun. So if a solar farm in Earth orbit could give you 100 kilowatts, that exact array at Mars might give you only 40 to 50 kilowatts, when clean and aimed well. To get the same output, you have to scale up. That means doubling or tripling the total panel area. For a serious colony, you're talking about thousands of square meters of panels spread out over fields that cover the equivalent of several soccer pitches, all made of fragile glass, coatings and wiring. Those panels have to be delivered, unpacked, deployed, wired, cleaned and repaired. The structure holding them has to survive dust, temperature changes, and mechanical wear year after year. And remember, all of that is before you even talk about the one thing that Mars is very good at, throwing dust on everything. Martian dust is extremely fine, almost like smoke in some respects, and it sticks to surfaces because it gets electrically charged. Even a thin coating on a panel can cut its power output by 10 to 30%. Over time, if you do not clean your solar farm, you watch your power slowly drop day by day. Then you have the big events, dust storms. Local storms are common, and global storms sometimes wrap the entire planet, turning the sky into a dirty orange haze. During those events, sunlight at the surface can fall to a tiny fraction of normal levels for weeks. If your main power source is solar, every major dust storm is like someone slowly closing a valve on your lifeline. You can try to sweep or blow the panels clean, you can mount them vertically to reduce build-up, you can use robots to keep them clear, but in the worst storms, there is simply not enough light. The arrays look large and impressive, but they are being strangled by the environment. In that situation, batteries drain faster, heaters run cooler, farms get dimmer, and your safety margin shrinks. This is why nuclear reactors keep coming up in Mars planning, because they ignore weather, and they do not care if the sky is dusty. A small fission reactor that can deliver tens of kilowatts, say 40 kilowatts of electric power, and run 24 hours a day, gives you a stable base load. That is enough to keep life support, computers, basic lighting and critical pumps running for a medium-sized outpost. Add a few of them, and suddenly you have a much more solid foundation. Solar can then act as an extra, not the core. The fuel for these reactors is loaded before launch. With good design, the fuel can last 10 to 15 years before you need to refuel or replace the core. That sounds like a long time, and in early mission timelines it is, but in the scenario we are talking about, where Earth goes silent and never comes back, that fuel lifetime turns into a hard deadline. 10 years after the cutoff, or 15 if you are lucky, that reactor winds down. To keep nuclear power after that, you need the ability to handle nuclear fuels on Mars, process or import fresh uranium or other fuel from local rocks, build or refurbish cores and deal with waste. That is basically a full nuclear industry with mines, refineries, fuel fabrication plants, strict quality control and a strong safety culture, all running on another planet with no outside help. So your power mix is a compromise. You probably have reactors for baseline, solar for extra, and redundancy, maybe some small wind use in certain locations, but all of it depends on one more thing: storing energy when it is easy and releasing it when it is hard. Mars has nights that are about 12 hours long, similar to Earth, but colder. When the sun goes down, your solar arrays go to zero. Your heaters now have to work harder, because the surface radiates heat away into space. Your air pumps and water systems cannot simply stop for half a day. People still need air and water. That means you need serious energy storage. For 100 people running life support, essential lights, communications, and some basic heating, you're looking at megawatt hours of energy to bridge each night safely. The kind of capacity that on Earth would sit in big industrial battery banks. You can store power in large lithium batteries in flywheels, or by making hydrogen and oxygen from water during the day and burning them in fuel cells at night. Every option eats materials, takes up space and has limits. Lithium batteries lose capacity a little bit every cycle, and they hate deep discharges, extreme cold and physical damage, all of which are risks on Mars. Mechanical systems like flywheels have bearings and control systems that wear out. Hydrogen systems leak, embrittle metals and need tight seals. With Earth in the loop, you just swap aging hardware. Cut off from Earth, every percentage of capacity you lose and cannot rebuild is permanent. Over years, your full battery bank might only hold 80% of what it used to, then 60%, then less. At some point, a long night or a storm shows you exactly how far it has declined. So when that power is tight, you start making choices. What do you shut off first? And how far are you willing to go down that list to keep people breathing and warm? In a power emergency, the colony will shut down non-critical loads. First go the big energy-hungry systems that are not directly keeping people alive, mining rigs, some industrial processes, non-essential labs, maybe entertainment systems. If that is not enough, you dim or cycle greenhouse lights, slow down pumps, lower temperatures in some areas, reduce lighting in corridors and workspaces. In deeper crises, you may turn off heating in personal quarters and move people into a smaller, better insulated core area, concentrating your limited power on one safe volume. At the very bottom of that list, the last things you try to protect are life support, basic communications and control computers. If you're forced to touch those even a little, every other countdown, for air, for water, for food, speeds up. Condensation changes, temperatures drift, some crops die back, some machines operate out of spec. People get colder, more tired, and more likely to make mistakes. Without Earth, there is no rescue ship coming if you miscalculate that trade-off. So far, we have treated power as the thing that keeps systems running, but one system stands out because it eats power constantly, has long delays between input and output, and directly decides whether your colony starves or not. If your energy grid is this fragile, what does that mean for farming on Mars? And can Martian agriculture really carry the entire colony when the last freighter from Earth has already arrived and gone? Start with the basic math. A typical adult needs roughly 2,000 to 2,500 kilocalories of food per day. In energy terms, that is about 8 to 10.5 megajoules. Call it 10 megajoules per person to keep it simple. For 100 people, that is about 1,000 megajoules of food energy you have to grow or unpack every single day. If your diet is fairly energy dense, you might get that from about 25 kilograms of dry food per day, around 55 pounds. That is not a huge pile when you see it once, but stretched over a year, that is more than 9 tons of food. Over 10 years, more than 90 tons. So can you just land that much food from Earth, stack it in storage and relax? Not if you're planning for a real cutoff. Picture a very generous starting cache. 20 tons of packaged food, freeze-dried meals, grains, oils, canned goods, at a total of about 2.5 kilograms per person per day, including water in the food and packaging mass. 100 people will burn through those 20,000 kilograms in roughly 80 days, under 3 months. In real planning, you would bring more, maybe enough for a year or two as a buffer, layered with local production. But even if you somehow bring 100 tons, that is still only about 4 years of full rations for 100 people, and that assumes zero waste, no spoilage, and perfect planning. Stored food is a timer. It buys you time to get agriculture running, to handle failures, to cover bad harvests. It does not give you an endless supply. When Earth goes dark, the countdown on every barrel and box is fixed. You can stretch it by cutting rations, but that just trades calories for time and health. Long-term survival means your daily food input has to come from Mars itself, not from warehouses filled by past launches. So what does farming look like on a planet that is cold, dry, and covered in toxic dust, with almost no air pressure? You're not going to walk outside and plough a field. On Mars, farming is an industrial process inside controlled spaces. The realistic picture is hydroponics and vertical farming, plants grown in nutrient solutions or thin substrates, stacked in racks under artificial lights. High-efficiency LED lighting for dense crops might use around 200 to 400 watts per square meter. For a 100-person colony, rough estimates say you could need something like 5,000 to 10,000 square meters of growing area, depending on crop choice and how close you push your yields. Take the middle of that range, 7,500 square meters. At 300 watts per square meter of lighting, if you ran it all at full brightness, that is about 2.25 megawatts of electrical power. In practice, you will cycle lights, use reflective surfaces, and optimize, but the point is clear. Your food supply is directly tied to your power grid. If your reactors or solar farms sag, your lights dim, your plants slow down, and your calories per day drop. Those farms also need pumps, nutrient mixing systems, temperature control, and humidity management. Every pipe, nozzle, and LED driver is another failure point. On Earth, you swap parts from a catalogue. On Mars, after cutoff, you repair what you can and rebuild what you are set up to manufacture. If your main greenhouse controller fails and you cannot replace its electronics, you are suddenly running your food factory in manual mode, with less precision, less yield, and more risk. People have already tested pieces of this idea. In the Soviet BIOS 3 experiments, crews lived in sealed habitats with plant chambers that supplied most of one person's oxygen and a significant share of their food, using only tens of square meters of crops per person. On the International Space Station, astronauts have grown lettuce, wheat, and other plants in small modular units, proving that plants can grow in space under low pressure and artificial light, if you control the conditions carefully. The lesson from all of those tests is not easy, it is possible, but fragile. Agile. The systems work when you have tight monitoring, plenty of sensors, and people constantly checking nutrient levels, light timing, and plant health. When a pump clogs on the ISS, a resupply ship can bring a new one. When a sensor misbehaves in a lab on Earth, a technician swaps it out that afternoon. On Mars, with no contact and no cargo, the same failure can mean a whole crop bed goes dry or floods, and you do not have the right spare on hand. That still assumes you can rely on liquid nutrient systems and plumbing. What about just using Martian dirt like soil? Martian regolith is not soil in the Earth sense. It is more like crushed volcanic rock mixed with fine dust and perchlorate salts, with no natural organic matter and no living microbes. Plants need structure, water, nutrients, and a web of microbes to break down waste and support root health. Raw regolith gives you almost none of that by default. To turn it into a growth medium, you have to wash out or break down the perchlorates, which are toxic to humans and can harm plants at certain levels. You then have to add organic matter, maybe from composted plant waste and human waste, and seed it with selected earth microbes. That is not a one-time job, it is an ongoing industrial process. You need bioreactors to grow microbial cultures, controlled composting systems, temperature control, mixing gear, and good analytics to watch chemistry inside your soil. Every batch of regolith you process consumes water, energy, and time. If you skip that work and try to plant directly in raw regolith, you risk poor growth, chemical stress on plants, and long-term health issues for anyone exposed to dust that gets into the habitat. Hydroponics and aeroponics avoid some of that soil preparation work by growing plants in nutrient solutions or mist, but they push complexity in a different direction. Now you are completely dependent on pumps, tubing, spray heads, tanks, and precise chemical recipes. A salt buildup in a line or a pump failure you do not catch in time can kill an entire rack of plants. You then need to flush the system, replace pipes, and rebalance nutrients. And you need a steady supply of those nutrients, which are made from nitrogen, phosphorus, potassium, and trace elements, all extracted and refined locally once Earth is gone. This leads to the most uncomfortable truth about Martian agriculture after cutoff. You do not have to fail often to be in trouble, you only have to fail once at the wrong time. Plants have lag. If a disease gets into your main calorie crop, say wheat or potatoes, and wipes out a big fraction of your production, you cannot fix that in a week. You can clean, replant, and increase planting density, but your next harvest is still weeks to months away. During that gap, you eat into your stored food. If the failure comes after Earth has already stopped sending ships, that storage is finite. If you misjudge, you can end up in a slow-motion famine, where rations get cut, people lose weight, and there is no clear way to recover to a comfortable margin. So when you look at food on Mars, the pattern is the same as air and water. The science says it is possible. The engineering shows ways to do it. but the margin for error, once Earth disappears from the equation, is thin. One sustained power shortage, one software bug in your greenhouse controls, one major contamination event, and your food security can flip from tight but stable to falling behind. And while all of that is happening, there is another countdown running in the background, one you cannot taste, see, or hear easily. It is not about calories, it is about the slow damage to your cells from the environment outside your walls. Even if you have enough food, enough water, and enough air, how long can your bodies, and especially your children's bodies, really tolerate the radiation and conditions of the Martian surface? Radiation on Mars is not a background detail. It is a slow, constant threat that never turns off. Even if your food, water, and air are stable, the environment outside your walls is always trying to damage your DNA. The real question is not, is there radiation? It is, how long before the total dose starts to break people down? Rover measurements give a clear number. On the Martian surface, the typical radiation dose is around 0.6 to 0.7 millisieverts per day. Over a year, that is more than 200 millisieverts. For comparison, that is on the order of 10 times higher than the natural background radiation in many places on Earth. It is also in the same range as a couple of full-body CT scans every year, for as long as you live there. Current astronaut career limits for radiation dose are based on staying below levels that push cancer risk too high. Long Mars missions, especially multiple ones, can chew through those limits quickly. Radiation dose adds up over time. Your cells repair some of the damage, but not all of it, and some mutations slip through. In a short-term mission, that increased risk might be accepted. Over decades for a whole population, it stops being an acceptable side effect and becomes a serious design constraint. If your colony is cut off from Earth and has to keep going for 30, 40, 50 years or more, you cannot just hope the numbers work out. You have to bring the dose down a lot. You do that by putting mass between you and the sky, and on Mars, that mass is the local dirt. Regolith becomes your main shield. If you build thin metal cans on the surface and live in them like Arve, radiation stays high. If you bury your habitats under 2 to 3 meters of regolith, about 6 to 10 feet, you can cut the incoming cosmic rays and solar particles dramatically. Model studies suggest you can push yearly doses down from over 200 millisieverts to something in the range of a few tens of millisieverts per year. That is still higher than many Earth locations, but it changes the game. Instead of almost everyone will get some radiation-related issue if they live long enough, you move into elevated risk but maybe manageable, especially with good medical care. The trade-off is construction. Moving that much regolith is a serious job. You need excavation equipment, structures that can carry the load, and good sealing. You also need to bury not just living spaces, but sleeping areas, medical rooms, and ideally any place people spend long stretches of time. Greenhouses might be semi-buried or built into trenches, with extra shielding on the sides. Tunnels, lava tubes, or underground caverns become attractive, if you can find or make them. Every meter of cover you add lowers your long-term cancer risk and protects electronics too, but each meter costs time, power, and hardware. Even with shielding, there is a different kind of radiation threat you have to plan for. The short, sharp spikes from the sun, the events that can give a lethal dose in hours if you're unprotected. Solar flares and solar particle events can throw bursts of high-energy particles at Mars. In those hours, the radiation level in space and on the surface, especially in thinly shielded areas, can jump. An astronaut caught outside in a light suit, or working in a lightly shielded greenhouse, can get a dangerous dose before they can react if no one warns them. On Earth, and in current missions, we rely heavily on constant monitoring from satellites and ground-based systems to spot these events and issue alerts. In a cut-off Mars scenario, you do not have Earth's vast monitoring network feeding you early warnings. The colony has to run its own space weather watch with its own instruments and models. You need hardened shelters, areas with extra thick shielding, where people can retreat for several hours or more during a major event. You need clear procedures, drills, and fast communication inside the colony. If one big solar storm hits while your key people are out in thin-roofed greenhouses or driving relatively unshielded rovers, and you miss it, you can end up with your farmer team or your maintenance crew taking a life-shortening or even lethal dose in a single day. If you handle the spikes and control the averages, that still only addresses the first generation. The harder limit appears when you start thinking in terms of children, an entire lifetime spent under Martian conditions. For the first wave of adults, higher radiation means higher cancer risk, more cataracts, more long-term tissue damage. Annoying, serious, but somewhat understood. For kids born and raised on Mars, you are entering unknown territory. They will grow up in partial gravity, around 0.38 G, with chronic low-level radiation as a constant. We do not have long-term human data for that combination at all. Animal experiments in orbit show that embryos and young animals can develop abnormally under high radiation or strange gravity conditions. Bone density, organ development, nervous system growth, all can be affected. So a Mars colony that starts having children is running a real, uncontrolled experiment on human development. Over 20 or 30 years, you might see shifts in average height, bone strength, immune function, and fertility. Some of those changes might be tolerable, others might create serious medical challenges. With Earth still in contact, you can at least get expert input, new drugs, new protocols. Without Earth, you're stuck with what you brought, and what your local doctors can invent. There are research directions that might help. Some drugs can support DNA repair or protect cells against radiation to a degree. Materials rich in hydrogen, like certain plastics or water-filled walls, block radiation more effectively per unit mass than metals, so you can build smarter shields. You can even imagine genetically modifying crops, or maybe eventually microbes, to act as partial radiation absorbers or to clean up reactive molecules inside the body. The hard limit in a cut-off scenario is that you cannot upgrade your tech stack easily. Whatever generation of radioprotective drugs, shielding materials, and medical imaging equipment you launch with, that is your starting point. If you did not bring the gear to produce next-gen pharmaceuticals on Mars, you will not get them. If your imaging systems age and cannot be replaced, early detection of radiation-linked cancers gets worse, not better. Radiation becomes a slow, cumulative invoice that the colony keeps paying year after year, whether it is ready or not. And while that slow biological damage is building up in bones and organs, another type of slow damage is happening in parallel in the hardware that runs your air, water, power, and farms. Because radiation and dust do not just wear down people, they also chew through electronics, seals, and pumps. If your bodies are running on a long radiation clock, your machines have their own clock too, measured in failures per week. So the next hard question is, on a dead Earth timeline, what actually fails first? Your cells, or the machines that keep your cells alive? On Mars, the scary part is not one giant failure, it is the constant stream of small ones. The whole colony depends on machines that were never meant to run forever, so the blunt question is, how often can things break before the whole system falls behind? The closest real example we have is the International Space Station. Up there, something in the life support chain is always acting up. Pumps in the air recyclers clog. CO2 scrubbers reach the end of their life and need their cartridges swapped. Urine processors jam or leak. Valves stick. Fans wear out. Crews spend a lot of their work time just keeping the station running, replacing filters, bolting in new parts, and working through long maintenance checklists. The safety net is simple but huge: regular cargo ships. If a component turns out to be unreliable, ground teams redesign it, make a better one, and launch it. If a filter type fails early, they send more spares. If a laptop dies, they replace it. The ISS is only a few hundred kilometers up, and it still eats a steady flow of hardware. Now move that idea to Mars, where the distance is tens of millions of kilometers, and a one-way trip takes 6 to 9 months in a good launch window, and then remove the cargo ships completely. That is your warning. The same rate of small failures with no resupply becomes a long, slow crisis. Every piece of hardware in your colony, from the biggest reactor coolant pump to the smallest fan in a sensor box, has a number behind it, the mean time between failures. Maybe a simple fan is rated for 20,000 hours. Maybe a pump is good for 40,000 hours. Maybe a valve actuator is expected to run 10,000 hours before problems appear. That is a few years of continuous operation at best. Now multiply that by thousands of components. Statistically, something is almost always reaching the end of its expected life. That is not a question of if, it is only which one next and how bad is it when it goes. The real survival question becomes very narrow. Do you have a spare part for that exact component? Do you have the tools and materials to install it? And do you have someone trained enough to do the job without making it worse? If the answer is yes for most of those failures, the colony keeps going. If the answer is no at the wrong time, you may lose one entire function, like a water recycling loop or a section of your greenhouse, and suddenly everything else is under more stress. That brings up something people underestimate, the human cost of just keeping all this hardware alive. Every maintenance job is time and energy pulled away from everything else. In isolated bases on Earth, like Antarctic stations, a large share of daily work is not research, it is basic upkeep. Clearing snow, fixing generators, repairing plumbing, checking air systems, keeping vehicles running. On Mars, the load is worse because every system is more complex and the environment is harsher. Realistically, especially in the early years, 30 to 50% of all human work hours could end up going into maintenance and repairs. That means half your people, half the time, are not doing new science, not expanding industry, not training. They are just stopping decay. If the workload is too high, things get skipped. Checklists get rushed. A clogged filter stays a bit too clogged. A funny noise in a pump gets ignored until it fails hard. The lifespan of the colony ties directly to how efficiently you can do maintenance. Better design, clearer procedures, and good training translate into real extra years of survival. Because of that, you do not design a Mars colony like a house that you patch as needed. You design it like a spacecraft that has to survive with no rescue. That means overkill and redundancy everywhere that touches life. You want triple redundant CO2 scrubbers, so if one fails and one is in maintenance, the third still keeps up. You want at least 2 fully independent water recovery trains, each able to handle most of the load if the other is down. You want manual backup valves for every automated control, so a software glitch does not lock a critical line closed. You oversize pumps and pipes, so they are not always running at their limit. You add extra tanks, extra sensors, extra cross-connects between systems. All that redundancy increases mass and cost at launch. It makes planning harder. But when the last ship from Earth has already landed, each extra independent path for air, water, and power is extra time on your survival clock. Redundancy buys you not just safety in emergencies, but breathing space to fix things correctly instead of in panic mode. Still, even with perfect design and endless checklists, there is a wall you eventually hit. Some types of wear cannot be stopped, only delayed, and some parts are so specialized that if you cannot rebuild them locally, that is the hard end of the line. Think about high-performance ball bearings in your pumps and motors, these special seals that keep high-pressure oxygen from leaking, the membranes in your water filters, the catalyst beds in your CO2 converters. These are not simple metal plates you can cut in a basic workshop. They rely on specific alloys, precise geometries, clean manufacturing steps, or complex chemicals. No matter how gently you use them, they have finite lives. They pit, crack, foul, or poison over time. At first, you replace them from the boxes of spares you brought from Earth. Maybe you have 10 sets, maybe 100. Decades pass, and one by one those parts go into service and then wear out. When you install the last spare of a critical component, you may not even notice. The true crisis comes when that last one fails, and you realize your local industry cannot fabricate a replacement that meets the required specs. No amount of clever hacking can make a failed high-pressure seal hold 100 bar of oxygen again, if you do not have the right polymer or metal. No amount of 3D printing can fake a complex multi-layer membrane if your printers and chemistry are too basic. That is the entropy wall. The colony does not usually die because everything fails at once. It dies when one component in one essential chain cannot be replaced at the required quality, and there is no workaround that keeps the whole system stable. Air stops being fully recycled, or water can no longer be cleaned fast enough, or a reactor cooling pump cannot be trusted at full power. You can throttle down, ration, and stretch things for a while, but eventually that missing part cascades into more failures. So the real survival question after Earth goes dark is not only how many spares did we pack, it is how much of our own machine ecosystem can we rebuild from Martian rock and atmosphere. If your weak link is a small exotic component, do you have the industrial tools to climb up to that level on Mars itself? And that pulls us straight into the next layer of the problem, because stocking spares only pushes the deadline a bit. True long-term survival demands something harder, building the factories, furnaces, printers, and clean rooms that let you fix the things you were never supposed to fix off-world in the first place. So the next tension point is clear. When the imports end forever, can a Mars colony build its own spare parts from scratch? Or does it quietly run down until the last irreplaceable piece fails? Real independence on Mars is not about how many rockets you launched. It is about whether you can fix the things that break, when Earth is no longer a store you can order from. The core question is harsh. When a critical part dies, do you have the ability to build a new one from Martian materials, or is that where the whole system stops? Start with the optimistic side, what you actually can do on Mars with a decent workshop. With good metal and polymer 3D printers, plus basic machining tools, you can make a lot of useful hardware. Brackets, mounting plates, ducts, simple gears, housings, piping, even some pressure-rated components if you test them well. Mars has iron, aluminum, silicon, magnesium, and other metals locked in its rocks and dust. If you can run a furnace at around 1200 to 1600 degrees Celsius, you can smelt regolith and pull out raw metal. From there you cast ingots, roll sheets, extrude bars, and feed those into your mills and printers. But that already assumes a lot. You need high-temperature furnaces with reliable insulation. You need crucibles that do not crack. You need molds that do not warp, cutting tools that can handle the alloys you make, and measuring devices to check strength and purity. None of that is one magic machine. It is a whole workshop culture, with people who know how to debug a bad casting, how to tune print settings, how to heat treat a part so it doesn't snap under load. You're trying to recreate, in miniature, the kind of metal working ecosystem that took centuries to build on Earth. For big items made of bulk metal or plastic, that is hard but possible. The real nightmare starts when you hit electronics. Here, Mars hits a wall. You are not going to be fabricating cutting-edge 5nm CPUs in a dusty Martian garage. Even making relatively simple chips like motor controllers, power transistors, or basic microcontrollers needs ultra-clean rooms, extremely pure chemicals, and lithography gear that can place features measured in fractions of a micron. That is heavy, delicate, and very power-hungry infrastructure. You could, in theory, launch a compact semiconductor fab to Mars, but protecting it from dust, radiation, vibration, and slow decay, then staffing it with enough experts is a massive challenge. If you do not have that level of factory, you are stuck with a finite stock of advanced electronics. Every control board in a pump, every sensor array, every radiation-hardened CPU in a reactor system has a limited life. When it fails, you either replace it from your stored spares, or you try to build a simpler local substitute. That substitute might be bulkier, less efficient, maybe it runs at lower speed, maybe it uses older, more forgiving manufacturing tech. But if you cannot design and build that clunkier but local replacement, then some systems remain forever dependent on the electronics you can only get from Earth. So your true independence is not limited just by metal supply. It is capped by how far up the electronics ladder you can climb on Mars. That gap between we can print brackets and we can build our own motor drivers and computers is one of the hardest bottlenecks in the entire survival picture. Then layer on chemistry, because a lot of what keeps your life support, farming and medicine working is not metal or silicon, it is molecules. Mars gives you the raw elements: carbon and carbon dioxide, hydrogen from water ice, nitrogen in trace amounts in the atmosphere, plenty of oxygen bound in rocks and in CO2, and a spread of metals. But useful stuff like fertilizers, plastics, solvents, refrigerants, cleaning agents, and instant pharmaceuticals are not just piles of elements. They are specific compounds that require reactors, catalysts, distillation columns, and carefully controlled conditions. If you want nitrates for fertilizer, you have to capture nitrogen and convert it. If you want polyethylene or other plastics, you need to turn CO2 and hydrogen into hydrocarbons, then polymerize them. If you want basic drugs, you need glassware, bioreactors, sterile rooms, and a library of reactions. Each new chemical process you set up reduces your dependence on shipped goods, but each one also adds complexity and more machinery that can break. Your survivable timeframe without Earth is now directly linked to how quickly you can stand up robust local chemistry. The faster you can go from we mix imported nutrients to we make our own fertilizers, solvents, and basic meds from Martian inputs, the slower your stockpiles run down. Early on, your industrial footprint might be small: a few 3D printers, a modest metal shop, maybe a basic foundry, plus some lab-scale chemical reactors. That is enough to improvise, to adapt some hardware, and to stretch spare parts. Long-term survival, though, demands a full web of industries. You need mining rigs to pull ore and ice, refineries to process metals and chemicals, machine shops to turn those into parts, bioreactors to make food additives and drugs, glassworks for windows and fibre, textile production for clothing and filters. Each time you add one of those capacities, you remove a class of items from your must-ship from Earth list. At some point, if a dust storm wipes out half your solar panels, your response is not panic and rationing, it is, fine, we run the panel line harder for a few months. We have the glass, the cells, and the frames. That is the level where your survival odds start to climb sharply, because the local disasters become repairable instead of terminal. But even if you build that web, your fate can still hang on one absurdly specific detail. That is the last irreplaceable part problem. Imagine your colony has done almost everything right. You smelt your own metals. You make your own plastics. You can build simple chips and robust power electronics. You grow food and recycle water. You even manufacture decent pumps, fans, and valves. But there is one component you never fully localized. Say a high-pressure oxygen valve that uses a special alloy and a very precise seal geometry. You brought 200 of them from Earth. Over 40 years, one by one, they go into service and wear out. You swap them, you track inventory, and then, eventually, you install the last one. 10 years later, that last valve develops micro cracks. It starts leaking under full pressure. You test it, you see it is unsafe. Now you need a new one. But your alloy furnace cannot hit the exact composition. Your machining tolerances are not good enough for the seal geometry. Your seal materials cannot handle pure oxygen at those pressures and temperatures without burning or cracking. You can try to overbuild, you can try to operate at lower pressures and accept worse performance, but maybe your whole life support loop depends on those specific specs. That single bottleneck can cascade. Maybe you lower system pressure to keep the old valve alive, which cuts oxygen output, which forces you to run other systems harder, which increases wear elsewhere. Maybe you lose that line completely and have to push everything onto a backup that was never meant to be permanent. In the worst case, that one missing piece sets off a slow failure in the whole air and water chain. This is why the survival of a cut-off Mars colony is not defined by its average level of independence. It is defined by the weakest, least replaceable link in its industrial chain. One exotic seal, one catalyst you cannot reproduce, one class of sensor you cannot print or assemble, can set the ultimate limit on how long you can function. And all of these factories, furnaces, printers, and labs, no matter how good, still have to fit inside structures that keep a breathable atmosphere in and the vacuum and dust of Mars out. You can build the best machines in the solar system, but if the walls around them crack or the floor under them shifts, everything they support goes with them. So the next question is blunt and physical. When your entire world is a set of pressurized shells on a shaky, cold planet, how long do those shells really last before the leaks, cracks, and quakes catch up? Your entire world on Mars lives inside a pressure bubble, and that bubble is always trying to tear itself apart. The walls are not decoration, they are the only thing between you and near vacuum. The question is simple: how long can those shells hold before physics wins? Your habitats are basically spacecraft bolted to the ground, made from aluminum composites, maybe some inflatables with rigid frames. Inside, you keep the pressure somewhere around 70 to 100 kilopascals, close to Earth's sea level. Outside, the Martian atmosphere sits at about 0.6 kilopascals. That is almost a full atmosphere of difference, roughly 10 tons of force pressing on every square metre of wall, about 1.5 tons per square foot. Every panel, weld and joint is being pushed outward all the time. Now add temperature swings. As the metal heats and cools, it expands and contracts a tiny bit. That flex is microscopic on each cycle, but it happens every Martian day, again and again for years. The same with bolts and welds. They carry load, relax a little, then carry it again. Over decades, that repeated stress can turn small manufacturing imperfections into real cracks. You do non-destructive testing, you inspect, you patch, but you are still fighting basic material fatigue. So even if you overbuild the first shells, you have to ask, what else is out there? Quietly chewing on your walls while that pressure pushes from inside. Mars hits you with a nasty combination: dust and thermal cycling. Day-night temperature swings of 50 to 70 degrees Celsius, about 90 to 125 degrees Fahrenheit, are not unusual. Metals expand when they warm up, contract when they cool. Polymers and rubbers that you use in seals and hoses do the same, but often more dramatically. They soften, then stiffen, then slowly harden and crack with age. On top of that, Martian dust acts like fine sandpaper. The particles are tiny, sharp, and get blown around at tens of meters per second by winds. They wedge themselves into gaps, abrade flexing parts, and get ground into seals. If a seal was supposed to stay flexible and airtight for 20 years, the combination of cold swings in temperature and dust might cut that lifetime in half. Every flexible seal or gasket that hardens a little, every tiny crack that opens when the structure shifts a fraction of a millimeter, adds to your leak rate. You might not even notice at first. The only sign is that your oxygen plant has to work a bit harder, or your stored gas tanks drain faster than the model said they should. By the time you see a measurable pressure decay, you may have dozens of small paths leaking air into the thin outside atmosphere. That leads to the next hard reality. What actually kills you first? A big explosive failure, or a slow, almost silent leak that nobody spots in time? A catastrophic rupture in a main habitat is obvious and immediate. A large crack or tear can drop pressure fast enough that people collapse in seconds and die in minutes. You design everything to avoid that, with safety margins, multiple layers, and strict inspection. But most real failures start small. A tiny puncture from a bit of debris, a hairline crack at a weld, a seal that no longer quite seals, and now you are losing millibars of pressure per day. On the ISS, astronauts have spent entire days hunting leaks that small. They close hatches, watch pressure gauges, listen with ultrasonic microphones, and eventually find a spot where a bit of foam gets sucked in. That is on a station with a few main modules. On Mars, your colony might have hundreds of meters of habitat walls, tunnels, and piping stretched across multiple modules and buried sections. Without Earth support, there is no replacement station coming. You will be chasing and fixing leaks forever. In practice, you may end up with a rolling pattern. Older shells that leak more get downgraded to storage or workshops where a slow pressure loss is manageable. Newer, tighter modules become living and medical spaces. You keep building new sections, moving people into them, and either patching old ones again and again, or cannibalizing them for parts. If your construction falls behind your leak problem, your safe volume shrinks. And all of that assumes the only forces on your structures come from inside pressure and daily temperature swings. But Mars is still a planet in space, so what about hits from above and shaking from below? Mars has an atmosphere, but it is thin. Small meteoroids that would burn up high above Earth can make it to the Martian surface at kilometers per second. The chance of one rock punching straight through your main habitat is low in any given year. But over many decades, with more structures and more surface area, the risk adds up. One unlucky hit could puncture a roof, damage an external tank, or shatter exposed equipment. Then there are Marsquakes. The InSight lander and other missions have already detected them. Most quakes are mild, but they prove that Mars is not completely dead inside. A stronger event, even if it is rare, can shift foundations, crack supports, or move tanks just enough to stress pipes and seals. A storage dome sitting on regolith might tilt a little, making its joints work harder. A buried tunnel could see its lining flex in ways it was not designed for. You counter that with good engineering, deep foundations, flexible couplings in pipes, and automatic shut-off valves for tanks. But a colony that has to last for a century without outside help cannot count on we got lucky. It has to be built for the occasional hit and shake. So you have a choice about how you build long-term housing. Do you keep living in thin cans and trying to patch them faster than they age? Or do you dig in and start turning Mars itself into your outer wall? Short-term imported metal and composite modules make sense. They arrive tested, they are pressurized quickly, you can expand fast. Long-term survival pushes you toward heavier, more permanent structures. You can bake regolith into bricks using solar or nuclear heat, and stack those into domes or arches. You can pour basalt-based concrete into molds, forming thick walls and ceilings. You can carve or use natural lava tubes, sealing and reinforcing them to make huge underground halls. If you put a few meters of rock or concrete over your head, leaks become less likely, radiation drops, and temperature swings smooth out. A wall that is 1 or 2 meters thick is not going to puncture from a tiny micrometeoroid. A buried structure flexes less under daily heat changes. You still need inner liners and seals, but the heavy shell outside is no longer operating right at the edge of its strength all the time. The trade-off is obvious, it is a lot more work up front. You have to move massive amounts of material, run heavy construction gear, and spend precious human hours building something that will not pay off for years. In a scenario where Earth is still supporting you, it is tempting to delay that kind of bunker-level investment. In a cut-off scenario, though, those thick buried spaces are what stand between your great-grandchildren and a long list of tiny cracks, so you can think of Mars habitats in phases. First, imported cans and inflatables, fast but fragile, then hybrid bases, where thin modules sit under regolith mounds or inside excavated pits. Finally, full planetary architecture, with regolith brick cities, concrete caverns, or lava tube complexes that can ride out centuries of dust, quakes and impacts with only incremental repairs. If you get to that final phase before your first generation shells wear out, your structural risk drops a lot. But even in the safest bunker, there is one thing you cannot build out of rock and metal: the human body itself. Your walls can be perfect, your air can be clean, your power can be stable, and you still have to deal with bones losing strength in 0.38 G, medicines expiring on the shelf, and children growing up in an environment no human has ever experienced. So once your metal bubbles are strong enough, the next hard limit shows up, not in steel or concrete, but in muscle, blood, and DNA. Can your medical systems, your drugs, and your understanding of human biology actually keep up with a multi-generation Mars colony that never sees Earth again? On Mars, there is no emergency flight to a bigger hospital. Whatever medical setup you land with is what you live and die with. Every serious case is a final exam, and failure often means someone does not walk out. Your hospital is basically a clinic scaled up as far as you can afford. A few rooms for exams, a small operating area with basic surgical tools, maybe an anesthesia machine, a sterilizer, some monitors. For imaging, you might manage a compact CT scanner if you're ambitious, or more likely ultrasound and maybe a simple X-ray. You'll have some lab capacity, blood tests, basic cultures, maybe a small gene sequencer if you really planned ahead. But that's it. No full trauma centre, no specialised burn unit, no backup ICU with dozens of ventilators across town. If a colonist gets crushed in a machinery accident, has a complex spinal injury or needs a major organ transplant, on Earth they might have a shot. On Mars, with a small team and limited gear, a lot of those cases turn into we keep you comfortable and do what we can, and sometimes that's not enough. So the risk picture shifts. Injuries that would be survivable on Earth become potential death sentences. Now add the problem that your medical tools themselves age out. Drugs, reagents and supplies don't sit on shelves forever. Most medications have real shelf lives. Antibiotics lose potency. Anesthetics break down. Insulin, vaccines, chemotherapy drugs, specialty hormones all drift or degrade over years, especially when exposed to temperature swings and radiation. Even if you store them carefully, your stockpile has an expiration curve. While Earth is still talking to you, you can keep shipping new batches. Once that link is gone, the pharmacy you have is the largest it will ever be, unless you build a pharmaceutical industry on Mars. Even a modest local pharma lab isn't trivial. You need very clean rooms, controlled temperatures, advanced glassware, reaction vessels, filters, and a steady supply of reagents and solvents. You need trained chemists and biochemists, not just smart people. You can't just wing antibiotic synthesis from a wiki page. You need real process control. If you don't manage that, your list of available drugs shrinks year by year. First, you run out of the rare ones. Then you start rationing the common ones. Infections that were simple to treat become dangerous again. Surgical risks go up. Cancer care drops back to crude methods. And some chronic conditions become unmanageable. Even if you keep the drug supply going, Mars changes your body in ways we don't fully understand yet. Gravity is one of those quiet forces we only really notice when it's gone. Mars gravity is about 3.7 meters per second squared, roughly 38% of Earth's. On the ISS in 0G, astronauts lose bone density and muscle mass even with heavy exercise programs and machines. Their hearts and blood vessels adapt to a world without weight. On Mars, partial gravity should be less extreme, but we do not have long-term human data. Not for 5 years, not for 20. Over 20 to 30 years in 0.38 G, colonists might end up taller on average, with weaker bones and more fragile joints. Their hearts and circulation could adapt to pushing blood in a weaker gravity field, which might make returning to Earth almost impossible physically. Everyday tasks will feel different too. Lifting a 50-kilogram object will feel closer to lifting 19 kilograms, around 40 pounds, but stomping or tripping might send you further than you expect. Your entire biomechanics baseline shifts, and medicine has to adapt to that new normal. Then you hit the biggest unknown of all. What happens when you try to have and raise children in this environment? We simply do not know if human embryos can develop normally in partial gravity with elevated radiation in the background. Studies on mice, rats, and fish in orbit have shown developmental quirks, including changes in organ development and behaviour. Mars is not 0G, but it is not Earth either. The first pregnancies on Mars, especially in a cut-off colony, are not routine events. They're risky experiments. If something goes wrong in fetal development, you cannot send the child home to better hospitals or to a safer environment. All the specialists you have are the few doctors and nurses you brought and trained. The colony leadership then faces a brutal choice: accept those unknowns or delay to stay safer medically and risk demographic collapse as the original adults age out with nobody to replace them. There is no safe answer, only trade-offs. On top of long-term changes, there's a faster, nastier threat you have to stay ahead of. Infectious disease in a sealed, small population. A novel pathogen in a confined environment is a serious nightmare. Everyone shares ventilation systems. Many people share bathrooms and workspaces. Quarantine space is limited. Your medical staff is tiny, maybe a handful of doctors and nurses for hundreds of people. A hard-hitting virus or a highly resistant bacterium could spread quickly before you even realize what's happening. The upside of being cut off from Earth is that you're also cut off from Earth's pandemics. No new flu strains, no imported respiratory viruses, no surprise from someone stepping off an airplane. But inside the colony, hygiene has to be ruthless. You need strict cleaning protocols, good air filtration, aggressive hand-washing culture, and a tight vaccination schedule. For anything you do have vaccines for, you keep coverage as close to 100% as possible, because losing 20 or 30 people in one outbreak is not just a tragedy, it can push your population below the level you need to maintain all your critical skills and industries. Isolation procedures have to be fast and decisive. Someone spikes a fever with odd symptoms, they get tested and are moved out of shared spaces quickly. You trace contacts. You might even lock down whole modules for days. That kind of response is stressful and disruptive, but on Mars, a slow or weak reaction can cost you the one thing you really cannot regrow easily: a stable, diverse population with the right mix of expertise. So by the time everything together, limited medical infrastructure, shrinking drug stocks unless you build a full pharma chain, bodies drifting away from Earth norms in 0.38 G, unknown pregnancy and childhood outcomes, and constant epidemic risk in a sealed box, the picture is clear. Even if your machines work, your long-term survival is limited by biology and medicine as much as by engineering. And none of that exists in a vacuum. All these pressures land on real people, in cramped spaces, under constant stress, with no way home. If the medicine can't keep up and the injuries pile up, how long before the mental strain, conflict, and simple human exhaustion start tearing at the colony from the inside? On Mars, the environment outside is lethal, but the environment inside your own head can be just as dangerous over time. The real test is not just can the hardware last, it's can people stay stable, sane, and cooperative for years with no way out? We already have hints from Earth. People who overwinter in Antarctica or serve long tours on submarines report sleep problems, depression, irritability, and a lot of interpersonal tension. And that's with internet, with the knowledge that a plane or a ship can eventually bring them home with real sunlight in some cases. In those places, you can still step outside without a spacesuit and not die in 30 seconds. On Mars, isolation is much harsher. There is a time delay on every message to Earth, so conversations are slow and awkward, and in a full cut-off scenario, that contact stops entirely. You look outside a window, if you have one, and you know that one bad seal, one broken helmet, is instant death. There is no airport, no port, no evacuation route. Your brain integrates that constant background threat, and it raises the baseline stress for everyone. People get shorter tempers, sleep gets lighter or more broken, and small annoyances hit harder. The size of your group changes how all of that plays out. With a crew of only 15 or 20, one nasty feud can poison the whole station. If two people can't stand each other, there's nowhere to go, you still have to see them at meals, in workspaces, in emergency drills, lose 3 or 4 people to burnout, injury or conflict, and you've cut a big chunk of your total skill set. Push the population up to 200 and the dynamics shift. Now you can have cliques and subgroups without the entire social fabric ripping. If 2 people hate each other, they can mostly avoid direct contact. If one key expert burns out, there's a decent chance someone else can pick up the slack. Models of small group behavior show that crossing that line from team size to village size adds a lot of stability. The price is obvious though. Getting a few hundred people to Mars with enough infrastructure to support them is extremely expensive and complex. And if Earth goes dark before you reach that cell, you are stuck trying to maintain social stability with a group that is statistically fragile. Layered on top of that is governance, because on Mars almost every decision ties directly to survival. There is no such thing as a harmless policy mistake. Every major argument is about resources that keep people alive. Do you allocate extra power to expand the greenhouse or the machine shop? Do you send more people to build new habs or to deepen your mining operations? When is it safe to increase the birth rate or to accept more medical risk for expansion projects? Every choice about risk, construction, exploration, or population growth feels existential, because it is. Without Earth in the loop, there is no external arbiter, no mission control that makes the final call. Whatever constitution, charter, or agreement the colony set up before the cutoff becomes the only framework you have. If that framework is vague, unfair, or easier to hijack, power struggles can break trust fast. Your conflict resolution systems, your election rules or command hierarchy, your norms about dissent and whistle blowing all become as critical as your oxygen recyclers. A power struggle that paralyzes decisions about maintenance or expansion can kill people just as surely as a bad valve. Then there is the sharpest psychological risk, the fact that one unstable person can cause physical catastrophe. High-stress isolated environments on Earth already see higher rates of depression and sometimes self-harm. On Mars, someone in a really dark place has access, in principle, to life-critical systems. One person opening an airlock at the wrong time, contaminating a water tank, disabling a control computer, or sabotaging a power bus can put dozens or hundreds of lives at risk. That doesn't just mean you need therapists and counselors. It means you need to design the whole colony around limiting how much damage any single individual can do. That looks like layered access control on critical systems, not just one person with a master password. It means physical interlocks on airlocks and valves, so no one can just walk up and dump atmosphere with a button press. It means logging audits and having more than one person sign off on major changes. At the same time, it means giving people trusted, confidential mental health support, because you want problems spotted early, not after someone has already decided they have nothing to lose. Over the long term, survival is as much trust engineering as it is mechanical or software engineering. All of that still isn't enough if life feels like unending grind. If every day is just fixing leaks, repairing pumps, and following procedures, people burn out. That's where culture stops being a luxury and becomes part of life support. You need shared rituals and real downtime, not just you can rest on Sunday if nothing is broken. Celebrations tied to Martian seasons, local holidays marking landings or milestones, regular communal meals, sports in low gravity, music, art, storytelling, all of that gives people reasons to stay connected. Over years, Martians will develop their own slang, their own humour, their own ways of seeing Earth and themselves. That emerging culture gives them an identity that is more than stuck on a rock, and that matters when something goes wrong and you're asking everyone to pull together one more time. A colony that loses its sense of purpose, that starts to feel like a dead-end trap instead of a long project, is fragile. In that state, one ugly argument, one unfair decision, or one failure from leadership can trigger resignations, non-cooperation, or even active sabotage long before the machines fail. So now all the limits are stacking: engineering, medicine, psychology, governance, culture. Even if you solve those, the planet itself still has one more layer of risk to throw at you. Mars is not geologically dead, not weather-free, and not safe from impacts. You've built a fragile civilization in a place with thin air, dust that can blanket the entire world, quakes that shake your foundations, and rocks that still fall from the sky. If all your systems and your people are running this close to the edge, what happens when Mars itself decides to throw a once-in-a-century storm or quake at you, and there is no Earth left to send help afterward? How safe is a planet that can turn off its own sunlight for months at a time? Mars looks still and empty from a distance, but for a small colony depending on thin margins, the planet itself is a slow, random threat generator. Start with the biggest gun Mars has: global dust storms. Roughly every decade or so, the atmosphere can get kicked into a feedback loop where dust lifts, warms the air. That warm air lifts more dust, and the process keeps going until the whole planet is wrapped in a hazy blanket. At ground level, sunlight can drop to a tiny fraction of normal, for weeks or even months. If your main power source is solar, that's not bad weather, that's a planet-wide blackout. In that situation, panels that usually give you tens or hundreds of kilowatts might barely trickle out a few percent of their rated power. Any rover, outpost or mining rig relying on local panels starts draining its batteries. Once those are empty, systems shut down, heaters cool, electronics freeze and lubricants thicken. Some of that hardware may not wake up again. Inside the main colony, you're leaning hard on reactors, fuel cells and long-duration batteries. If you didn't build storm-hardened infrastructure with enough non-solar power and storage to ride out weeks of low light, this is where your survival clock can suddenly jump forward from decades left to days left. Even if you get through the blackout, storms don't just kill power, they also throw dust into every gap and coat every surface, which accelerates wear and raises your maintenance load right when you're most tired. So Mars can choke your power grid, but what about the ground under your feet? How stable is the crust you're bolting your life to? Data from landers show that Mars does have Mars quakes. Most are small, but they prove the crust moves. Habitat modules, tanks, tall antenna masts and towers need solid foundations and flexible connections. If you cheap out on that or misjudge local geology, a moderate quake can tilt a tank, crack a connection, or stress a pressure shell in ways it was never designed for. On Earth, if a quake damages a building, you bring in heavy machinery, concrete trucks, and specialist crews to rebuild. On Mars, your concrete might be hand-mixed from baked regolith, your cranes are few, and your repair teams are already busy keeping day-to-day systems running. A crack in a propellant tank or a slow leak in a buried pipe might not get fixed fast enough because you simply don't have the manpower and materials. Every structural margin you don't build in up front, you pay for later, in higher risk after every shake. The ground shifts, the sky goes dark, and then there's the third hazard that doesn't care where you live: rocks falling from space. The probability that a civilization-ending asteroid hits your colony directly in the next 100 years is tiny, but it's not absolute zero. More realistically, smaller impacts are the concern. A several-metre-wide rock slamming into the ground tens of kilometres away can kick up local dust, throw shockwaves through the ground, and launch secondary shrapnel. If you've got solar farms, fuel depots, or relay towers out on the plains, some of those could eat fragments, crack panels, or puncture tanks. Your best defences are boring but effective. You bury as much critical infrastructure as possible, especially fuel, air, and water storage. You keep sensors watching the sky for near misses and incoming objects. You spread out key systems so one impact can't kill them all at once. That way, a local impact might cost you some gear, but it doesn't turn into a full colony emergency. Even when nothing big hits or shakes, the Martian atmosphere still plays tricks. It's thin but not empty, and that creates its own set of wildcards. Mars air is less than 1% of Earth's sea level pressure, so the wind doesn't hit with the same physical force. But high-speed gusts can still move dust, sand, and lightweight structures. You can get local dust devils, temperature inversions, and CO2 frost forming and sublimating with the seasons. Those effects can create sudden, localized wind events you didn't fully expect. Your weather models are based on a short observation record, just a few decades of spacecraft data versus centuries of Earth measurements. That means your 100-year storm estimates are weak guesses. If you underbuild wind bracing for your towers, underestimate how much dust a certain slope can dump onto your hab roofs, or size your air intakes wrong, a surprise weather pattern can overload something you thought was safe. On a planet where every repair is slow and every failure hurts, those miscalculations add up. So you're designing for a world where the sun can fade for months, the ground sometimes moves, small rocks still fall from space, and the air plays games with dust and temperature. How conservative do you have to be if there's no Earth rescue on the table? The honest answer for a cut-off colony is brutal. You design for the worst case you can reasonably imagine, not for the average day. You assume multi-month global dust storms. You assume rare but strong Mars quakes. You assume that a big solar storm might hit during a period of hardware stress or partial failure. You layer your defenses so that a storm plus a quake plus a minor human error still doesn't kill you. That means extra centimetres of shielding over your HAB roofs. It means thicker pipes, more braces on tanks, more anchor points for towers. It means triple redundant power feeds to critical systems, so one broken cable or melted connector doesn't take down life support. It means more storage of water and air than looks efficient on paper. Each of those choices costs mass and work up front, but each one is a bet that when the once-in-a-century event finally hits, you're among the colonies that limp through it instead of the ones that vanish. By now, you can see a pattern. Mars applies slow stress through radiation and dust, random hits through weather, quakes and impacts, and constant pressure on every system you build. You respond with thicker walls, more redundancy, and smarter planning. But there's one more layer where failure is even more final, and it doesn't crack or leak, it just quietly disappears. Once Earth is gone, all the knowledge you didn't bring and all the software you can't patch are gone with it. Your hard drives, Tavivas and code bases stop being tools and start being the last copies of entire skill sets. So the next question is, when something breaks that you've never fixed before and the manual is corrupted or missing, does your civilization stall out there? Once Earth is gone, every server, rack and hard drive in your colony stops being just IT gear and turns into the last backup of an entire civilization. Hardware you can sometimes rebuild. Knowledge you lose is just gone. The question becomes, how long before your software and documentation decay enough that you start forgetting how your own systems work? Almost everything in a Mars colony runs on software. Life support controllers, mining rigs, greenhouse systems, reactors, power inverters, medical devices, rover fleets, all of it. Those codes were written by teams on Earth, in specific languages with specific libraries, build tools and assumptions. In normal life, when a bug shows up, you file a ticket, wait for a patch, update the firmware and move on. In a cut-off scenario, whatever version you have on the day Earth goes silent is what you get, probably forever. Bugs that were scheduled to be fixed in the next release are now permanent features. Config files that only one engineer on Earth fully understood are now sacred texts. If an update you pushed right before the cutoff had a corruption or a hidden bug, you may discover years later that one specific sequence of actions bricks a critical subsystem, and there is no vendor to call. On top of that, storage isn't immortal. A single failed SSD, a controller fault in a RAID array, or a bad sector on the OneDrive holding a particular firmware image can mean you literally no longer have a clean copy of the code that runs, say, your CO2 scrubber controller. You can reverse engineer some of it, sure, but doing that under time pressure with lives on the line is very different from doing it in a relaxed lab on Earth. So one of the most valuable cargoes you bring isn't tanks or machines, it's information. Terabytes and terabytes of how to do things. In a serious Mars plan, you'd preload the colony's data system with complete offline repositories. Engineering manuals for every major subsystem, medical textbooks, guidelines and surgical references, chemistry databases for reactions, materials and safety, agriculture guides for hundreds of crops, pests and nutrient setups, open source software mirrors, encyclopedias, design blueprints, training videos. The more you cache before the cutoff, the fewer times your future self has to reinvent 500 years of science, one experiment at a time. When a pump fails and you can't get the exact model anymore, having full spec sheets and old catalogues lets you design a drop-in replacement. When a strange infection shows up, having decades of Earth medical data gives your tiny clinic a fighting chance to identify it and pick a treatment. When you want to set up a new chemical process, having full reaction pathways and process notes can save you years of dangerous trial and error. You won't have live Earth experts, but you can still bring some of their brains with you in another form, local AI and expert systems. You can train models on Earth before launch, specialized AIS for tasks like diagnosing mechanical faults from sensor logs and vibrations, designing mechanical parts that meet certain loads, or helping doctors narrow down diagnoses and drug doses. Once they're on Mars, those AIs sit next to your engineers and medics, helping them think faster and scan more options. They're like having a panel of consultants that never sleep, but they share the same problem as your software in general, they don't get updates. If a critical bug exists in your AI doctor and it only shows up in some small fraction of cases, you might not notice until it confidently suggests the wrong treatment for a condition that looks familiar but isn't. If a control system AI has a rare failure mode, it might push a reactor or battery bank into a dangerous corner of its operating range at exactly the wrong time. Without Earth, you can't ship logs back for retraining or get a patched model. The only fixes you can make are the ones you can do locally, with the data and compute you have. That means you need people who actually understand what these systems are doing under the hood, not just users clicking buttons. Even if your software and AIs are perfect, the storage they live on is not. Digital memory is fragile over decades. Hard drives have moving parts that wear out. SSDs can suffer from charge leakage and controller failures. Optical media can cloud or delaminate. Cosmic rays and background radiation can flip bits in memory cells. Over a few years, with redundancy and backups, that's manageable. Over multiple decades with limited replacement hardware, you're eventually forced into a new role. Your colony becomes a scriptorium, copying and recopying its own knowledge. You'll need routines that regularly scrub data, check for corruption, and mirror critical archives across multiple devices. At some point, you may find that the only truly long-lived way to store absolutely essential information is not digital at all. Printed manuals, carefully kept, paper copies of wiring diagrams, etched metal plates with reactor startup sequences, life support schematics, and emergency procedures. Those low-tech backups won't hold terabytes, but they can outlast your fanciest server when the last controller board fails. Because when you lose knowledge, you don't just lose trivia, you lose concrete capabilities. If the only surviving document that described how to recalibrate a certain CO2 scrubber is on a drive that died, that ability is effectively gone. You might try to reverse engineer the device, but that takes time, people, and lab resources you might not have. Each forgotten or corrupted procedure shrinks what your colony can do. Maybe you stop being able to run one kind of reactor at full capacity and have to downgrade. Maybe a particular medical imaging device can no longer be trusted, so diagnosis gets less precise. Maybe a complex production line can't be retuned after a big maintenance job, and its output quality drops permanently. Over generations, if you can't maintain your knowledge base with as much discipline as you maintain your air and water, your colony doesn't just diverge culturally from Earth, it risks slowly sliding backward, technically. Tasks that were once routine become black box mysteries. New kids grow up knowing less about how their systems work than the generation before. At some point, you're living in infrastructure you can no longer fully maintain, like inheriting a factory with no manuals and no teachers left. So you're fighting two battles at once, stopping physical entropy in your machines and stopping informational entropy in your knowledge. Beating both is what turns a fragile outpost into something that can last centuries. Failing either one sets a hard limit on how long your colony can perform at its original level. And that leads to the biggest question of all, not just how long can this one base hang on, but when does the scattered set of habitats and workshops cross the line into a full civilization that can truly stand alone? How many people, how much industry, and how much surplus do you need before Mars is not just surviving Earth's silence, but has genuinely become its own world? There's a big difference between a group that's stuck on Mars and a society that's from Mars. The line between those two is not poetic, it's population size, industry, and margin. How big and how built up do you have to be before Earth can disappear and you still keep going? Start with sheer headcount. A crew of 30 or 50 is agile and easy to launch, but it cannot carry the full range of skills a complex civilization needs. You can't have 3 neurosurgeons, a full surgical team, 5 chip designers, a cluster of nuclear engineers, specialized farmers, teachers, industrial chemists, and still have enough mechanics, builders, and leaders in a 50-person group. Everyone ends up wearing too many hats, and there is almost no redundancy. If your one experienced reactor engineer dies, retires, or burns out, you don't have a backup. Models of self-sustaining human groups suggest that for real stability, you want at least a few thousand people, Think 3,000 to 10,000. At that scale, you can support multiple layers in each specialty. You don't have one doctor, you have a clinic team and a hospital team. You don't have one software engineer who vaguely knows everything. You have people who specialize in power systems, life support, robotics, and networks. So a 50-person crew is an expedition. A 500-person base is a large outpost. A 5,000-person city is the start of a real self-supporting Martian civilization. The problem is, getting from dozens to thousands takes multiple waves of launches, years of construction, and a lot of luck that Earth does not go dark halfway through that build-up. Even with enough people, headcount alone doesn't give you independence. You also need economic loops that close on Mars itself. Early on, your economy is linear. You import machines, food, parts, and tools from Earth. You use them up. You export almost nothing back. To become independent, you have to flip that into circular flows, where most of what you consume is made locally, from local inputs, and your waste becomes input for something else. That means food comes from Martian greenhouses, not cargo holds. Construction materials come from regolith bricks, basalt concrete, and locally smelted metals, not aluminum cans landed by rockets. Basic tools and simple electronics are built in your own factories. You recycle metals, plastics, and organics, and you route industrial byproducts into other processes where possible. Closed ecological experiments like Biosphere 2 proved that even just closing the environmental loop, air, water, and soil was hard. Doing that plus industrial loops is even more difficult. You're trying to close cycles not just for carbon and nitrogen, but for copper, rare earths, polymers, catalysts, and more. Until most of those flows are internal, you're still critically dependent on the last shipment you got from Earth. Once Earth is out of the picture, your trade network shrinks down to Mars itself. But it's still a network, not a single base. In a mature setup, mining outposts send ore and ice to refineries. Refineries send metals, chemicals, and gases to factories. Factories send parts to habitat builders, vehicle yards, farms, and power plants. Farms send food and biomass back into cities and bioreactors. Waste treatment plants send clean water and recovered materials back into circulation. Every major node is a supplier and a customer for several others. If one link breaks, say a specific catalyst production line goes down, the whole web feels it. Maybe fertilizer output drops, so agricultural yield dips. That feeds into food rations. Or a failure in a glassworks delays new solar panels, which slows power expansion, which limits how much new industry you can power. Building robustness here means multipath trade, more than one source for critical goods, some local stockpiles, and the ability to reroute flows when a node is offline. That's how you turn a scatter of fragile outpost into a resilient planetary system. To keep that web alive across generations, you need more than machines and trade. You need an education system that's treated like infrastructure, not an afterthought. On Mars, every child grows up in a world where a busted pump or a misread gauge can kill people. That means education can't be optional enrichment. It is part of life support. Kids have to learn not just general science and math, but enough practical mechanics, biology, programming, and emergency response that a large fraction of the population can step into technical roles if needed. Your independence timeline is basically the half-life of your complex professions. If it takes 15 years to train a top-end nuclear engineer or a high-level surgeon and you lose 2 in an accident, how fast can you grow replacements? If your education system is weak and you can't train new experts faster than older ones retire, move on or die. Your capability curve points down. First you lose the fringe skills, then you lose depth in core areas. Eventually you may still have computers and reactors physically present, but nobody who fully understands them. So you need layered education, apprenticeship programs in workshops, formal schooling, on-the-job training in every critical system, and deliberate transfer of know-how from older to younger generations. Your university is not a nice-to-have. It's the factory that produces the people who keep the air breathable. Even with enough people, closed loops, and good education, you're not truly secure until you move from survival mode to surplus mode. In survival mode, you are always one failure away from trouble. You grow just enough food, run just enough power, and produce just enough parts to keep up. There's no slack. If a harvest fails, if a reactor has to go offline for months, if a key factory floods with dust, you are instantly in crisis. You cut rations, ration power, postpone maintenance, and hope you get through it. Surplus mode looks different. You produce more food than you eat and store the excess. You generate more power than you need on an average day and dump the extra into long-term storage. Your factories can make more critical parts than you're currently consuming, so you build up deep reserves of valves, bearings, membranes, chips, and tools. You have enough engineering and scientific bandwidth to run long-term R&D projects that don't have an immediate payback, like better radiation treatments or more robust crop strains. That surplus is what lets you overbuild habitats, thicken shielding, and tolerate hits from storms or quakes. It's what lets you absorb a bad year without immediately slipping toward extinction. A surplus Mars can think in centuries. A just barely surviving Mars is one crop failure, one big storm, or one chain reaction hardware failure away from a death spiral. So when we ask, how long could a Mars colony survive without Earth? What we're really asking is, how far along this path did they get before the line to Earth was cut? Are they a 40-person outpost? A 400-person proto-city? A 40,000-person industrial civilization? Because each of those starting points gives a very different answer to the final question, the one you probably had in mind from the beginning. If Earth went dark right after the last ship landed, are we talking months, decades, or centuries before Mars follows it into silence? So after all of this, where does the clock really land? How long could a Mars colony actually last once Earth goes silent for good? Start with the worst case realistic setup, an early outpost. You have maybe 30 to 50 people, some hydroponic racks, a few greenhouses, a couple of reactors, a big solar field, basic workshops, and a lot of crates full of imported electronics and spares. You can grow some food, recycle most of your water, and make a few simple metal parts. But core systems, advanced chips, complex valves, medical supplies, and key software support still depend on Earth. Earth goes dark. At first, everything looks normal. Your food and air still flow, your power is steady. Then the slow grind starts. Within months, one truly critical system takes a hit. A pump, a CO2 scrubber, a reactor component, a greenhouse controller, something where the exact replacement part is limited or already used. You patch, you cannibalize non-essential systems, you move hardware around, you shut down labs to free up gear, you cut power to some habitats. You can stretch a lot with good improvisation. Maybe you downgrade comfort, let temperatures float, accept lower pressure, eat more basic rations, and live in a smaller footprint. That might buy you a couple of extra years, but statistically, with that many components running near their limits, entropy wins quickly. The first unfixable failure might show up in year 1 or year 5, but it will come. In this scenario, months to a few years of survival after cutoff is a serious, honest estimate, not pessimism. Now look at a more mature case, a colony that had time to grow before the link to Earth was cut. Say you have a few hundred people, robust greenhouses that can cover most of your calories, multiple reactors, large battery banks, and a diversified solar network. You've built decent local metalworking, some chemical production, and maybe basic circuit manufacturing for simple electronics. You have real hospitals by Mars standards, better shielding and multiple habitats, some of them buried. Here, when Earth goes silent, you're not immediately on the edge. Kids grow up, get trained, and step into technical roles. Your agriculture can handle some shocks, your water system has local ice mines, your air system has multiple production paths. You can handle a major component failure by building workarounds instead of just scavenging. But you still have deep tech bottlenecks, advanced electronics, high-end medical imaging systems, some reactor internals, certain catalysts, specific high-pressure components, and a lot of specialized drugs, all remain tied to a finite stock. As those stocks age and shrink, you start to lose the ability to fully repair or replace some systems. So you downgrade them, run them at lower output, or retire them. Over 20, 30, maybe 50 years, you see a slow glide path. First-generation colonists die off. Second and third generations inherit a slightly less capable industrial base unless you've pushed hard on local high-tech industry. You might replace some Earth-grade devices with clunkier Martian-built versions, but not all. Eventually, one of the deep bottlenecks, reactor fuel, chip fabrication, complex meds, catches up with you. At that point, you may still live on, but at a lower technical level with more risk. In this intermediate case, a few decades of functioning, recognizable high-tech civilization after cutoff is plausible. Maybe longer if you planned well, but without deliberate effort to close those deepest gaps, you're trending downward over time, not holding steady. Now stretched to the extreme best-case scenario. Here, you didn't build a base, you built the seed of a whole world. You arrive with thousands of colonists, not dozens. You land tons of heavy industrial equipment, not just labs and habitats. You already have functioning heavy industry on Mars, including refineries, large-scale manufacturing, serious chemical plants, glassworks, textile production, and yes, at least a basic semiconductor fabrication capability. You have several nuclear reactors with fuel stocks planned for many decades or centuries, large solar farms, and huge energy storage systems. Your habitats are thickly shielded, partly underground or inside lava tubes. You've already rehearsed full closed-loop life support on Earth for years before committing to this. You also front-load information and training, massive data archives, local AIs, strong education systems, and deep stockpiles of strategic elements and rare gear. You know which parts are hardest to replace, and you have either learned to make them locally or brought absurd numbers of spares. In that world, when Earth goes silent, Mars doesn't just hang on, it can plausibly outlive Earth by centuries. Local industry can replace almost all failed components. New generations of engineers and doctors are trained entirely on Mars, with enough depth to keep the system going. Surplus food, surplus power, and surplus manufacturing capacity give you buffers against storms, quakes, bad harvests, and social shocks. That does not make you invincible. You're still limited by planetary hazards and long-term radiation effects, by culture, by accidents and rare disasters. But your survival window is now measured in hundreds of years or more, not in months or decades. Mars becomes a real branch of human civilization, not a fragile off-site project. There's a brutal twist under all of this, the Martian paradox. To become independent from Earth, you first have to be massively dependent on Earth. A self-reliant Mars doesn't start with a lean, heroic camping trip. It starts with thousands of tons of hardware ferried across space, reactors, machine tools, construction robots, entire factories, massive archives of data, and lots of people. It starts with overkill, with triple redundancy, with way more capacity and stockpiles than you need for normal operations. The more you front-load industrial capacity, knowledge, and spares before the cutoff, the longer your no resupply clock runs afterward. If you try to do Mars on the cheap, with a small crew and minimal infrastructure, your independence time is short. If you treat it as the largest infrastructure project humanity has ever attempted, your independence time expands dramatically. So when you ask, how long could a Mars colony survive without Earth? There is no single number, there's a curve. A small early outpost with 30 to 50 people and partial self-sufficiency, you're looking at months to a few years before some unfixable failure or cascading shortage forces a terminal decline. A mid-scale, well-prepared colony with hundreds of people, good greenhouses, strong power, and serious local industry, you're in the range of decades, maybe several, with a slow drift downward unless you've nailed the hardest technologies. A fully industrialized Martian civilization with thousands of people, heavy industry, deep stockpiles, and robust education, you're in multi-century territory, limited mainly by Mars's own hazards and your ability to stay socially stable. The deeper shock is that nothing in physics or biology clearly forbids that best case. The obstacles are scale, planning, and will. If we treat Mars as a stunt or a camping trip, a cut-off colony dies quickly. if we treat it as an all-in planetary scale build-out from day one, then in a far future disaster where Earth goes permanently dark. The last human lights might not be blue and green at all, they might be the dim, stubborn glow of cities under the red sky, still running long after the radio fell silent. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.